Hey everybody. So in the last one we were talking about complex numbers and we were looking at them algebraically, right? As numbers that you can add and subtract, multiply and divide. And we're still thinking of them that way, but we're going to add a little something to this. So let's start by thinking of our regular numbers, right? So if we look at our real numbers, sometimes we use this symbol for the real numbers. Oops, the set of real numbers. We often picture this set of numbers on a number line, right? So there's our number line. Maybe we put 0 somewhere, right? And we can tick off our positive ones to the left or to the right, and our negative ones to the left. And there are some, besides just visualizing what the numbers are, there are some nice geometric consequences of thinking of it this way that help us with some of the algebraic things. For instance, if I start with the number 1, right, if that's my number and I perform an operation on it, a function like the function that adds 2 to it, when we get 1 plus 2, we move this number over to 3, right? So you can think of addition as like shifting your number, moving it in place. If I take a number like 1 and multiply it by 4, we could think of this as like its distance from the origin is 1. When we multiply it by 4, we stretch its distance from the origin out 4 units, right? We don't usually think this way. The geometry isn't as convenient or helpful for us, though it's not a bad way to think about things. One other way we often think about things is another geometric way, for instance, is like when we have negative numbers, or any number really, we can think of its absolute value, right? Which we sometimes might say is making it positive. It's a piecewise function is another way to say it. It multiplies negative numbers by -1 and leaves positive numbers alone. But another notion of it is that it's its distance from the origin, right? So whether you're positive or negative, how far you are, right, isn't a negative thing. -3 is 3 units from 0, right? The negative tells us what direction, but if all we're caring about is distance, then we just want the number 3, right? So I'm beginning this way because we're going to do a very similar thing with complex numbers. We're going to introduce some geometry to picture them. And this geometry is going to let us think about certain kinds of operations in different ways. With complex numbers, the geometric intuitions are much more valuable and much more interesting for us than these are, but they're it's sort of a similar idea. So let's jump into that. Let's look at some complex numbers. Recall that a complex number is a number that can be written in the form x plus iy, where x and y, we'll use a symbol here. That just means they are in the set of real numbers. So x and y are real numbers. And I is one way we sometimes say this is the square root, the principal square root of -1. Okay, so that was our complex numbers. So what we often do with complex numbers, we don't think of a number line. They are still numbers, but because they're a little different in nature, remember they have a real part and an imaginary part. And again, don't let the word imaginary make you think that these aren't interesting or useful and they're just made up things to torment you with math. They're very useful and have plenty of applications in the real world. But this is just a name, a traditional name. So our complex numbers have these 2 parts. We can't really put them on a single number line, right? We can't think of one as being greater than another, things like that in the traditional way. So what we do is we plot them on a coordinate system. Right, the coordinate system that you've seen before, or at least visually looks the same. It's got a horizontal and vertical axis. I guess visually is how things look the same, or looking the same is visual. And for any complex number z, we will write it, we will place it in this coordinate plane by x plus iy will correspond to the point x, y. So you look at the real and imaginary part and use them as coordinate points. So we think of this as the real line, right? Which is really just a copy of this line right here, right? It's all of our numbers, zeros in the middle. And this is going to be our imaginary axis. All right, so we got a real axis, which is like our real line that we're used to picturing numbers on, and we have an imaginary axis, which is vertical. And so when you have a complex number, it's going to have a real part and imaginary part. You plot you take those real and imaginary parts and make them the coordinates and plot them in the usual way. So for example, let's look at 2 points. Let's look at z is equal to 1 plus I root 3. This is going to correspond to the point 1 root 3 because this is the real part, this is the imaginary part. Right? There's our real part, is in the horizontal position, there's the imaginary part. So that point on this plane that we do call a complex plane will be, let's make it, I'm just thinking about my scale, I'll use the dots. So 1 unit over for the real part, root 3 units up, that's about 1.7. So there's our point z. All right, let's do one more. Let's look at w. What did I have for w? W will be -5 root 3 over 2 plus I times 5 over 2, right? So this will correspond to the point -5 root 3 over 2, 5 over 2. So out here, let's see, there's 2.5 up, and we're going to the left. It's a little harder to estimate, somewhere about right here, I believe. I'm eyeballing this, right? Those numbers, 2.5 up, this number to the left, that's going to be our point W. Okay, so there's our first piece of geometry for these, so we can picture these things in the plane. If you recall in an earlier video, another thing we like to do with numbers in the plane, which is going to turn out to be very useful for our complex numbers, is think about describing these with polar coordinates, right? Z is at some angle off the horizontal. Let's call this theta 1. And it's some distance away from the origin that I can call R1. W is some other theta, I'll call it theta 2, and some other radius away. And we can describe our complex numbers in the polar form, just like we did when we were just describing any points in the XY plane, right? So let's remind ourselves a little bit about that. So if we have a complex number, z equals x plus iy, then we take this and we get a corresponding point in the complex plane, right? We're in rectangular coordinates. But we can rewrite this as r theta using polar coordinates. Remember that our relationship is r squared equals x squared plus y squared. And theta is tangent inverse of y over x. And then if you are, we'll do this in another color. So it depends if you are in quadrant, if theta is in, if your point is in quadrant 2 or quadrant 3, you have to add this plus pi, right? Remember about the domain or the range of inverse tangent will always give us angles in quadrants 1 and 4, but sometimes if our point's over there, we have to add pi to rotate around. So that's how we convert to our polar coordinates. Also recall we have this relationship, x equals r cosine theta, y equals r sine theta. So this was how we converted back from polar coordinates to rectangular coordinates. What it does in complex numbers is gives us a new way to write them down. And that is as follows. So we start with this. This is going to be what we call our rectangular or maybe Cartesian form. Okay. We can replace x and y with r cosine theta and r sine theta, or you may want to factor out that r. Okay, and we call this the polar form of our complex number. Okay, and so this turns out to be a very handy way to write down our our complex numbers. Excuse me. And we won't do it in this video. We'll do some examples of how to write this. We start to see some of the geometric consequences of putting these complex numbers in the complex plane and what happens when you multiply, add, those sorts of things with them. We get some really neat consequences. But for now, we just want to, all we're doing is converting just like we did when we had polar and rectangular coordinates. We're converting the x and y, the real and imaginary parts, into r and theta and using them to write our numbers in this form. Now, there's one other form I want to write down for you that I'm going to offer with very little explanation. I'll do a couple of things in some other videos that might help convince you that this is a reasonable thing to write down. But this is an old discovery. It is definitely true, despite the fact that it looks very strange. Another way we can write down the same number is as follows. R, as written up here, but now we're going to do an exponential. E and our exponent is I times theta. Okay? I mean completely that these are all representations of the same number, right? It is completely justified to write r, z is equal to r e to the I theta, which is the same as r times cosine theta plus I sine theta, or if we convert to the rectangular form that way. They are the same thing, okay? So for now, we can think of this as a notation, but we can also think of it as a number, and all the rules of exponents that we know about will turn out to apply. So we'll talk more about that later, okay? So this we will call our exponential form. Right, specifically this first thing I wrote down, r e to the I theta, right? So given a complex number z equals x plus iy, we can write it this way by finding r and theta, just like we did in polar coordinates, and we write it this way, and we are representing the same number that is plotted in the exact same place in the complex plane, okay? Okay, one more definition, and then we'll do a couple of examples with those numbers we had earlier, z and w. Recall when we put these things in the plane, right? So if I put a point in the plane, so this is my real line, this is my imaginary line, this is some complex number, maybe I'll call it z. So remember, we had absolute value, which we think of making something positive, or that's often how people think of it. We make things positive. If they're already positive, we leave them alone, right? That's not the best way to think about it. A better way might be that for real numbers, it's a piecewise function that multiplies negative numbers by negative, and it leaves positive numbers alone. Now, a really great way to think about it is how far is a number from the origin, right? What I showed you earlier, -3, the absolute value is 3 because it's 3 units away. Well, we're going to use that idea now to come up with a notion of absolute value, or at least use the same symbol. We'll call it something a little different, but that this is the connection that we're going to use the absolute value symbol to represent how far a complex number is from the origin, which of course we've also been calling r. If this is theta, r is the radius, the distance from the origin. So our definition is, right, absolute value of z is, we'll say absolute value, or this is perhaps a better term, the modulus of z, and it is exactly r, which we know how to find. Given an absolute number, absolute value, complex number, x plus iy, the absolute value is just the square root of x squared plus y squared. It's distance from the origin, which is exactly r, the radius. Okay, so we can use this symbol that we recognize as absolute value with that geometric interpretation that it just means how far is something from the origin. Okay, and that's our definition of this modulus for complex numbers. Okay, so let's finish off with a couple of examples just to clarify these ideas, hopefully, before we get into the really interesting geometric properties in the next few videos. So these are the numbers, the examples I had before. W equals -5/2 root 3 plus I times 5/2. There's our two numbers. So let's do a few things. Let's compute for each of them the modulus. So the modulus of z is going to be the square root of 1 squared plus the square root of 3 squared, right? This is my x plus iy. This is the square root of x squared plus y squared in there. And that, of course, is 1 plus 3, the square root, 1 plus 3 is 4, and the square root of that is 2, right? We'll take the positive here because we're talking about distance. So there's the modulus of z. The modulus of w, it's a little bit uglier. So we have -5/2 root 3 squared plus 5/2 squared. What do we get? This is the square root. So we've got 3. The square root of 3 is squared. The 5 is squared. So we get 25 times 3 or 75. The negative goes away when we square it over 4. Here we get 25 over 4, which is, of course, 100 over 4, or 25, which is 5. So the modulus of w is 5. Okay. Let's convert these to polar form. So z we can think of as the point 1 root 3. In polar form, so I'll leave that as an exercise for you. This is just using the formula theta equals root 3 over 1. We end up with theta equal to pi over 3. So this is just the same exercise we did in converting to polar coordinates. We already found the radius of z, so our theta for this is 2 pi over 3, right? So this is our rectangular coordinate. This is the same point in polar coordinates. Let's do the same thing over here. We have -5 over 2 root 3, 5 over 2. We can convert this and get that theta. In this case is 5 pi over 6, again using theta is equal to tangent inverse or inverse tangent of y over x, in this case plus pi because this point is in quadrant 2. That's how we get this number. So we get our polar form. We already have the radius, r, which is the same as the modulus, the distance from the origin, which is 5, and we have our 5 pi over 6. Okay. And finally, we can write these in exponential form. Let's write them in polar and exponential form. This can be written as z equals r cosine pi over 3 plus I sine of pi over 3. And w can be written as 5, there's our r, cosine of theta, which is 5 pi over 6, plus I sine 5 pi over 6. And we can write them as r e to the I theta, in this case 2e to the I pi over 3. And w is going to be 5e to the I 5 pi over 6. Okay, So the last form, this exponential form, certainly looks the strangest to most of us at first glance, but in my opinion is often the most convenient. Though there are times all three of these turn out to be useful ways to write down some of these numbers, okay? And we graph them in just the same way, right? As we graph them before using our polar coordinates, we can use we graphed them before with our rectangular coordinates, we can use our polar coordinates now. Z ends up, right, its radius is 2, the angle is pi over 3. It would be 2 units out along this line. So I'm just making up a scale. There would be my point Z. You don't actually need the line in there. Oops. And then the point W, 5 pi over 6 is out in this direction. We want to go 5 units out. So if that was 2, somewhere out here, my scale's not perfect, there would be our point W, right? So just how we, these should be equivalent to, my scales are not great, right? I was grading these by hand, but they're more or less in similar places, right? Okay, so I think my scale's quite off on this. That angle was not quite right. I think Z should be, our Y coordinates should be below. So my scale's quite off, but just understand that we do the same thing, R and theta. The radius goes to where it's supposed to go. Sorry, the theta goes around the circle in the traditional way, in the conventional way, and then you go out on the radius that far. Okay, so this was mostly definitions, and it's really just leveraging the work we had already done on converting to polar coordinates. So if you need to review that, that would be a great thing to do now. And so we can take these rectangular forms of our complex numbers and write them in polar form. And then we have this mysterious other notation of the exponential form that turns out to be useful. And we'll dig into some of the consequences of all this, these forms and the geometry associated with them in the next video. Okay, that's it. Thanks, everybody.